Welcome to lesson 30. So we're going to talk about doing a t-test or t-confidence interval in a matched pairs setting. So the first thing we're going to do is try and clarify, what do we even mean by matched pairs? So in general, we assume populations are independent if each sample comes from completely separate populations. So an individual is sampled from one population doesn't have an opportunity to be sampled from a second population that you sample from. So they're in different unrelated populations. So you're probably looking at scenarios where you don't have people that are genetically, related to one another, or twins, or that sort of scenario. So we're actually going to focus on, in particular, when the populations are dependent, specifically paired. So maybe there's more than one measurement on a particular experimental unit, or you might have a pair that's related in some way. So one of the most common ones is going to be like a before and after, pre and post. Like when you test on twins, when you test on maybe like piglets that are in the same litter because they're genetically similar. When you split a unit to impose more than one treatment. So I know I used to get paid to be in experiments at a place back in Montana, and they were testing an ink on one arm and a different ink on another arm. And the idea is that's paired because the way my skin reacts to one ink is probably related to how my skin reacts to the other ink. So here we have a couple of studies. So study 1, we're interested in looking at how the attitude changes towards stats over the course of a semester, which we don't even have semesters. So a professor takes a simple random sample of their students. They give a questionnaire at the beginning of the semester, and then they give that questionnaire again at the end of that semester. So what do we think? Independent or dependent? So the key here, yes, they have before and after. However, it's the same students doing it. So how student 1 answers the first questionnaire is probably related to how they answer at the end of the term. So these are dependent. This is a classic before and after. And then here we have study 2. So at the end of a term, the stats professor wants to compare the general attitude towards stats for 2 different sets of majors. So they take science-based majors. How they determine what that is, I'm not entirely sure. And non-science-based majors. And they go ahead and take a sample from each of those groups. And we're assuming that nobody's double majoring and that they're somehow in science-based and non-science-based. So here they go ahead and they give the questionnaire to each of the students they select from both groups. So I would say these are independent, but I would throw in an asterisk, given that you're not sampling from students who are in both, right? So as long as these 2 populations that they're sampling from don't have any overlap, that's fine. So if you go ahead and you throw out all the students who are in both and only sample from students that are in one or the other, that would be fine. Okay, so here's an example. We have a before and after survey that we gave, probably on a Likert scale. So like on a scale from 1 to 10, how do you feel about such and such? So we have 13 randomly sampled students. So we have the first one is just student A, student B. This is just so we know that we have unique students. They're just labels. So then there are a couple of different ways we could look at this. If we went ahead and we looked at before and we looked at after, but we weren't careful to keep them paired together, we lose some information here. So you can perform what is a 2-sample t-test, which if you go on to ST202, we do not cover the 2-sample t-test in 201. And it looks like there's not a significant difference from the beginning to the end of the class on average, it doesn't look like, there was a big old difference. However, if instead you focus on the differences, this is us just running an analysis on just the differences. So here is a box plot showing just the differences. And if you think about it, if there was no change in attitude, you'd be looking at 0, right? But if the average difference is higher than 0, that sounds like if it's after minus before, there was an improvement, that the attitude increased, or it totally depends on what you're measuring with. But we did find that there was a significant difference when we looked at it this way. So we had a p-value of 0.02. So absolutely, if you're performing an independent like 2-sample t-test when it should be paired, you can definitely increase, especially your type 2 error. And it decreases the information that you have. If you're going to want to keep this before with that after, you want to keep this before with that after, you retain more information. Okay, let's look at some notation here. So we're going to use this example here. Here are my differences. So specifically, we did after minus before. You could have done the other way around. It's really important to specify like which one's higher, or what order of subtraction you have. So we're going to call these differences, like this is difference 1, this is difference 2, and so on. So when it says, DIs, it's really just all the way through D13, right? Because there are 13 of them. There's difference 1, 2, 3, all the way through 13. And D bar, that is if I took just these differences here and I took the mean of them, the average. So if I averaged those differences, that's D bar. And then this notation, S with a lowercase d here, I might have uppercase too, but that's the standard deviation. So if I went ahead and I threw just the differences in the calculator and asked for the standard deviation of those values, that is the standard deviation of the differences in the sample. And then ND, that's just saying, okay, well, how many pairs or differences? There are 13 students in this. So like here, ND is 13 in this example. So using that notation, now we're going to set up how we would put together the confidence interval and or hypothesis test. So for the confidence interval, so we're going to use this when we want to estimate the average difference. So when we have two paired or dependent populations and we want to estimate the average difference, this is when we would use this type of test. So we still do have conditions. We're going to stick to the 3 here. This is pretty much always going to be true. We're going to always want to have representative samples. And the easiest way to get a representative sample is to take a random sample. And then we want to know that based on the central limit theorem, that the number of differences that we have is going to be big enough for the sampling distribution of D bar. So not X bar here, but D bar to be approximately normal. So we want to know that the population of all the differences that could exist out there in the population, if that's roughly normally distributed, we definitely want to have a large enough sample size. And then the last condition here, the populations are dependent or they're paired. So if we want to do a confidence interval, the setup is still going to be what did I see in the sample, so D bar, plus or minus, you'll do a T star times your standard error of the D bars. So that standard error of the D bars, that's just going to be the standard deviation from the sample of the differences over the square root of the number of pairs that you have. And your degrees of freedom, it's just going to be your total number of differences minus 1. So one way to think about it is we're essentially doing our one sample t methods, but just on the differences. So instead of putting both of those like after and before, we're only dealing with the differences. Okay, so for the t-test, when we want to not estimate, test, when we want to test that average difference between two dependent populations. So a lot of times we might want to go, hey, is there a difference, or is that difference higher or lower? Usually than 0. That is usually what we're looking at. But so we're going to have the same conditions here as we did for the confidence interval. We want representative samples. We need to have enough pairs so that we could reasonably assume that the central limit theorem kicks in for the sampling distribution of d bar. And then we're going to have paired data. So we can look at, so the big thing that changes here, this delta not, this is saying this claimed difference, usually it's 0. It's almost always 0. It's very rare when that difference isn't 0. So the mean difference being equal to usually 0 versus maybe you think it's less than 0 or greater than 0. And the big difference between these two here, it matters so much which order you subtract it in. You need to keep track. Is it after minus before or before minus after? Because improvement in score, it's totally going to depend if it's positive or negative, like the order you subtract it in. And then you can do a two-tail test as well. So the setup here, it's going to be a t-statistic. So the average difference that you saw from the sample minus the claimed difference, usually 0. So usually you end up with just d bar on top, over the standard deviation of the differences, divide by the square root of the number of pairs you have. And then once you calculate that t-statistic, you're going to compare it to a t-distribution that has that n minus 1 degrees of freedom. So here's an example here. We have a university instructor. They want to assess how effective a particular lesson is. So they go ahead, they give a quiz at the beginning before they've given the lesson, and then they give an analogous quiz, I guess, after the lesson has been completed. So they want to go ahead and estimate the average difference between before and after scores using a 90% confidence interval. So what's really, really handy here, we're going to assume the population of score differences is normally distributed. So that's handy. That's going to be handy for that does the central limit theorem kick in question. So we're only taking 4 scores. That's why this is really, really necessary. So we have 4 students. So student 1 scored a 3 before the lesson, and they scored a 9 after they took the lesson. Student 2 got a 5, and it went up to a 7. So hopefully, I'm sure the instructor's hoping that their understanding of the material improved. I would hope that they increased. So differences. So specifically, this is after minus before. And it's really important that we keep track of which order the subtraction happened. So 9 minus 3 is 6. 7 minus 5 is 2. And a lot of times in stats, we just subtract in the order that gives us fewer negative numbers, but it doesn't matter. We could have subtracted in the other direction. It would be exactly the same results. So here, if I want to estimate it, my question of interest, this is going to be very similar to before. We're going to want to hit so what is? So for an estimation or confidence interval problem, what is? And then the average or mean, change. So here we're looking at a change in score. I wrote after minus before here. I really can't stress, it's very enough. it's really important that you make it very clear which way you're subtracting for all students in that lesson. So on average, like, what was the average change that end score that we saw for all the students in that lesson? Although admittedly, 4 is a very small sample size. So here, my parameter of interest. So it changes up if you're doing paired. So it should be the mean difference, so mu d. So it's the mean difference in quiz score after minus before for all the students in that lesson. So here, just to look back, 6213. So 6213. These are my differences, right? So we can take these 4 and find the average, and that'll be d bar. So the average change in score from that sample. You should get something like a 3. And since it's a score, you can put points, but it's not so important to use units here. A lot of times, like IQ scores or just scores in general, they often don't have the units included. So definitely plugging these into the calculator. I wouldn't calculate the standard deviation by hand, but when you do that, it's something like 2.16. You can keep going, but probably round at some point. It's kind of long. ND saying, okay, well, how many students did we have? There were 4 students, so we have 4 differences, so ND is 4. And so the degrees of freedom are n minus 1 or 4 minus 1, which is 3. So our degrees of freedom, they're a little small here. And you can kind of tell you pretty much aren't going to want to use t-methods. If you only have a sample of 1, it's not going to work out. Degrees freedom 0 is not a thing for us. So my confidence level, right here, 90%. My degrees of freedom, we just said were 3. So I need to find my t star. So t star is equal to, and then let's find it. So for me, my degrees of freedom are 3, and I want 90%. So degrees of freedom 3, that means I want this row. 90%, I'm going to look at the bottom. Okay, here's 90% here. And looks like here's my t star. So my t star, when I have 3 degrees of freedom for a 90% confidence interval, it's 2.353. So I'm not going to use 1.645 because I can't use the Z methods, but I can use T methods. So now we're going to check our conditions. So did we have a random sample? So basically, how are these students sampled? So here, sounds like all the students took the quiz before and after, but they took a random sample of their students looking back. So they randomly sampled 4 of those students. So in this case, yes, it was a random sample. And then we want to know, is the sample size large enough? So ND is equal to 4, which is pretty small. But since the population is normal, so the population of the differences are normal. So I would say this is okay. This is reasonably met. 4 is kind of it just is a little uncomfortably small, but 4 should be okay if we know the population is normally distributed. And then here, oops, this was a copy and paste. We can have access to the standard deviation, the differences. It is paired. So we have paired data, right? So student 1's before is paired with thereafter, right? You don't want to mix and match. You don't want student 1's score, paired with student 4's after score, that kind of thing. So I would say these are reasonably met. So filling these out, this was 3. I'm going to just write I'm not going to write all the digits here. 2.16. So ND was 4. My degrees of freedom was 3. This was 2.353. So now I have everything I need to plug in here. So 3 plus or minus 2.353 times 2.16. I went ahead, I think I put all the digits into my calculator. Over the square root of, oh, this is nice, 4. Because that'll just come out to 2. So then, let me see. I get something like 3 plus or minus 2.54153. Obviously, you could probably do some rounding, probably to at least 2 places. So then I end up getting my 90% confidence interval for mu d. So the mean difference, it's going to be 0.46, I'm going to round now, to about 5.54. And if you want to put units, I might put points, but it's really not necessary to use units in this particular instance. So things to note, both of these values are positive, and we did after minus before. So if after minus before gives me a positive number, that implies that they scored higher afterwards on average than before. So this is good, right? We want them to score higher after the lesson than before the lesson. Otherwise it would imply the lesson's really not doing so great. So here, the 90% confidence interval for the mean change in, it was weird because was it attitude or quiz score? We'll say quiz score. And quiz score of all students in that lesson is on average estimated to be between 0.45 points to 5.54 points. And here's, I'm going to higher after the lesson. I need to imply, is it higher before or after? I could write that I did the mean change in quiz score after minus before. You could write it in there after the lesson. But it needs to be clear, was it higher before or after? So with a point estimate of 3 points higher after the lesson. So it can be a little awkward to word it. But here, so the 90% confidence interval for the mean change in quiz score after minus before of all students in that lesson is on average estimated to be between 0.45 points to 5.54 points higher after the lesson, with a point estimate of 3 points higher after the lesson. So very, very important to also make sure that you describe the order that you subtracted in. So now, same information, we're going to have this university instructor. They want to assess how effective that this particular lesson was. So they gave a quiz at the beginning and they gave a quiz at the end, and they randomly selected the 4 students. But now they want to test whether there's evidence the instructor's lesson was effective. So did students score higher after the lesson on average? So one way to think about it, if we have after minus before, if we want to know that it's higher than 0, you can add before to both sides. That would be after is higher than before. Right? So this is what we want. And so we want to know pretty much on average, is the average quiz score change higher than 0? If that average quiz score change was higher than 0, that implies that on average people scored higher points after the lesson. So my question of interest, if I'm doing a test, remember it's supposed to be kind of worded as a yes-no question. So here is the average change in score, so after minus before, for all students in that lesson higher than 0, which is a little goofy, right? So, I mean, a translation, which doesn't have all the, like, this alone wouldn't be enough. On average, did the quiz scores improve? So that's kind of translating, what does this whole first sentence mean? This is kind of just the layperson's term, like, on average, did they improve? So you could even say, is the average improvement in score, on average, did they improve? That kind of thing. And it looks like we're going to use a significance level 0.10, which isn't too surprising here because we did do a 90% confidence interval. So my parameter of interest, it's going to be the same parameter from last time. So that mean difference in quiz score after minus before for all students in that lesson. And then inventory, this is going to largely look the same. But then here, so my null is that the mean difference is equal to 0. So remember mu d, that's going to be after minus before. Right, so it's the mean difference specifically after minus before. My alternative, mu d, is higher than 0, right? Because if after scores were higher, then after minus before should be positive. So this is my null claimed value is 0. Almost always this is going to be, this will be 0. Every once in a while it's not, but it's not very common that it's something besides 0. So my significance level is 0.10. So we're going to check our conditions again. So here, I'm going to fix this right off the bat. Are these dependent paired? Yes. Right? So the first before score goes with the first after score. That's the same student's scores. That kind of idea. Is my sample size large enough? I have 4 pairs, which isn't very big, but the population we said was normal. So a sample size of 4 should be okay. Although we're not thrilled, 4 is very small. Then it was a random sample of students. So it sounds like this instructor, they gave all the students this quiz before and after, and then they randomly sampled 4 of them. So state my hypotheses. So I kind of got ahead of myself there. The null, so UD, so that's my mean difference. And by default, we're going to say it's equal to 0. And then my alternative, so I'm still going to want UD, still going to want 0. So difference, oops, it's after minus before. So we want positive numbers. If we see positive numbers here, that means they improved. So the alternative is higher than 0. So this is going to be a one-sided test. So that means that once I get my t statistic and find my one-sided p-value, then I'm done. I don't need to multiply by 2. So here we go. We have all of our parts here. This should be d bar. So when I need to plug in, so what did I observe? I observed a mean difference of 3. So that on average, the scores of those 4 students, they increased by 3 points after the lesson, which is good. You want it to increase, not decrease. It's bad news if it decreases. So divided by that 2.16, I didn't actually round in here, and then square root of 4, which is really nice. So doing some math here, I get something like 2.777. I'm just going to round it to 2.78. And it's positive, right? So, because 3 is higher than that 0. Okay. So here, we want to know the probability that a t statistic with 3 degrees of freedom is higher than that 2.78. 2.78. In general, if this is a positive number, we usually want higher than. If it's a negative number, we usually want lower than. Every once in a while, that's not true, but most of the time it's true. So what I need to do, my degrees of freedom are 3. That tells me which row I need to find. So I need the degree freedom 3 row. And then I need to find where 2.78 is. Chances are it's between 2 of these numbers. So like 2.78 is not between 0.7 and 0.9. It's not between 1.6 and 2.3, but it is between these two, right? So I would argue that my p-value is going to be between 0.025 and 0.05. So 0.025 is the smaller one. And please be very cautious, like we want you to put the smaller one on the left. So my one-sided p-value is between 0.025 and 0.05. And things to note, if I had a large enough t-statistic that it ran off the edge, if you're looking at these p-values, they're getting smaller and smaller. You could say, so like, let's say I'm going to pretend I had a t-statistic of, I'm going to make this up, 13. So see how 13 is higher than that? That would mean my p-value is less than this amount, 0.005. Keep in mind, you do not want to round to 0. It makes us very sad. So please don't round your p-value to 0. A p-value of 0 implies that what you saw in the sample is literally impossible. But you saw it in the sample, so it's not impossible. So we don't like p-values of 0. It makes us sad. It's totally fine to say p-value less than a small number. So here, I have a p-value of, so when I plugged it into my calculator, I found that it was 0.0346, which is between 0.025 and 0.05. So with a p-value between 0.025 and 0.05 at the 10% significance level. So either way, wherever the p-value is in this range, it's still less than 0.10. So we're going to reject. So considering I have a p-value between 0.025 and 0.05, that's fairly strong. It could be moderately strong, but strong is okay here. So we have strong evidence to suggest that on average, quiz scores improved. After the lesson. So, I mean, hopefully that kind of goes along with what we might expect, and we hopefully that we'll see that their understanding the material became better after the lesson. But yeah, so on average, it looks like they improved for people. Well, so after the lesson for all students that took lesson. So for all the students in that lesson. So you can definitely talk about like, oh, the average difference is higher than 0, but then you're going to need to translate like this means that the scores were higher on average after they took the lesson than before. So types of t-methods. There's 2 that we really covered here. There's another we'll mention. So in general, the parameter we're looking at is for means. So if you're doing with anything besides means, t-methods is not for you. And it's a scenario where we don't know the spread of the population. So we don't know sigma. So in the case where we have one population, we're going to use a one sample t-test. So that was that first set that we looked at. Then we have 2 populations. And if you have 2 populations, then you have to ask yourself, well, are they dependent or paired? Or are they 2, there's no overlap, independent populations from one another? So if you have independent, then you're going to go with a 2 sample t-test, which if you go on to Stat 202, we won't in 201. So then what we covered here, maybe you have dependent, this is dependent or paired. And so if you determine that, yes, I have paired data here, you're going to do a matched pairs t-test. So you're going to do a t-test just on the differences. So we looked at this one and we looked at this one. Know that this exists and it's really a common test that's used, but we won't have time to really cover it before. Okay, so that's it for lesson 30. Next up, we're going to talk about robustness, which kind of gets into, well, how reliable are these t-methods results?